Hello, this is Dr. K. In this series of videos, you'll be introduced to the Java programming language. These videos are partly based on chapters 1 and 2 of the book Big Java, the 6th edition by K. Horstman. Let's start with a question. What is programming? For that matter, what's a program? And what does a program do? Also, what runs a program? Okay, that's more than just one question. But if I give you 5 seconds, do you think you can answer the question that you see here? What is programming? You can pause the video if you like, but I'll give you 5 seconds starting from now. Okay, I'm not sure that this would be Horstman's answer, but here's one answer. Programming is the act of telling a computer what to do in such a way that a human can understand it. If you think about it, a programming language, especially a high-level language, is really meant for human beings. Some sort of compiler or interpreter is being used to translate that high-level language into the machine-level instructions that computers can understand. I'm guessing that most of you recognize what this is. It's a motherboard. It's the hardware inside your desktop or your laptop computer. On this motherboard, you can see that there's a place for the CPU, memory or RAM, disk drive, power cables, input, output, and extension slots. And I'm a little embarrassed to say that there's also a place to connect your floppy drive, which should tell you something about how old this diagram really is. But what's interesting is that the basic layout of the motherboard has not really changed too radically since floppy drives became obsolete. And by the way, something you don't see here is the system bus. That comprises the wiring on the motherboard that connects all of the components that we just mentioned. If I give you 5 seconds, can you tell me what these components are? 5 seconds starting from now. Okay, in the upper left there is a CPU. Underneath that is a RAM module or a memory module. In the upper right you see a graphics card, and below that you see a disk drive for storage. Now, my laptop still has a disk drive that looks like this, but many computers nowadays have a solid-state drive. The solid-state drives are more expensive, but they're faster and they don't have any moving parts. When a computer program is not running, it resides in storage. When the program is run, it's loaded into memory and the instructions are executed by the processor. Graphics cards, like the one you see here, will have their own processor that is dedicated to executing graphics commands. These are peripheral devices. They're used for input and output. I'm sure you could name all of these if I gave you 5 seconds to pause the video. So 5 seconds starting from now. Okay, from the left to right, top to bottom, we have a headset, a monitor, speakers, a scanner, a keyboard, a printer, a pen tablet, and a mouse. This is a picture of one of the first computers, the ENIAC, that was operational in the 1940s and used thousands, 19,000 vacuum tubes to perform its calculations. So, okay, here's another question for you. Can you tell me what computers use now instead of vacuum tubes? I'll give you 5 seconds starting from now. Ready? The answer is that transistors have taken the place of vacuum tubes. This is the main reason that modern computers have become so small. Intel has developed a transistor so small that 30 million of them can fit on the head of a pin. Let's look at a very simplified timeline of computer languages that starts sometime in the 1940s and goes up to the start of the 21st century. Something that's not in this picture that does deserve mention is Ada Lovelace and the Babbage engine. Nearly a century before electronic computers came into being, Charles Babbage designed a working computer out of mechanical parts, and Ada Lovelace configured it to do various calculations. So you often hear Ada Lovelace referred to as the very first programmer. And in fact, women were also the first programmers of electronic computers. As we've already seen, the ENIAC was the first general-purpose electronic computer. Well, it turns out that the ENIAC programmers were women. In the 1940s, female math majors were common, and during the war, many were hired to do things like calculate trajectories of rockets, usually by hand. 6 of these amazing women were hired to program the ENIAC. The link here leads to a short video at the Computer History Museum that shows excerpts from an interview with Jean Bartik. Let's take a look.
Betty Snyder and I, from the beginning, were a pair. And I don't know many of you work technically, but I believe that the best programs, the best design, and all this stuff is done by pairs, because you can criticize each other and, find each other's errors and use the best ideas, and it really works very well. Later on, I have thought about why did Betty and I become so successful? And we were successful. And I think it's because we were finishers. Because most people like to do the fun part of a design or a program, but they hate doing the nasty little details that usually take more than the middle design. And so you have to take care of everything and think of everything so that it works. Well, I was good at it, but Betty was even better than I am. She was fantastic.
A quote from Betty Snyder Holberton.
Oh, yeah.
Look like a girl, act like a lady, and work like a dog.
Wait a minute. You skipped a line.
Oh, I skipped a line. What?
Think like a man.
Oh. I don't know, though. I think you all were doing some great thinking there. Great thinking.
The smartest thing we did was to have Marlon and Ruth calculate a trajectory exactly the same way the ENIAC did it, add time by add time. Well, this is the document that made people respect us. Because of those 18,000 vacuum tubes, we could find the one that wasn't working in a very few minutes with that. And people never recognized, they never acted as though we knew what we were doing. I mean, we were in a lot of pictures, but they never asked us anything. Well, we did all the programming for it. I mean, it was absurd.
What a great video. Did you notice she talked about working in pairs? This was more than 50 years before the term pair programming became popular. How about when she talked about her and Betty being finishers? This is like the Pareto principle in software engineering that says that 80% of the effort is spent on the last 20% of the code. And to top it all off, the notion of high-level programming languages was non-existent at this time. In fact, these women were coding by figuring out what wires went into which plugs in order to come up with the correct calculation. That's pretty amazing. Assembly languages were the first real programming languages. They were very low level, allowed you to have full control over hardware, and were finely optimized for the particular processor you were working on. The blue box on the right gives an example of a factorial program written in assembly language. As an example of how this works, the third line of this program is telling the computer to move the long integer in register 5, which is a memory location on the processor, into a special register named EAX. As you can see, it's quite tedious to write this code, but it was better than having to physically move wires around every time you wanted to do a new calculation. The 1950s saw the introduction of high-level languages, languages that abstracted away things like memory locations and CPU registers. Three famous high-level languages are given here: Fortran, Lisp, and COBOL. Despite the success of these high-level languages, assembly language continued to be used when you wanted speed and efficiency, something only fine-grained control over the hardware could give you. But in the 1970s, Ken Thompson developed the UNIX operating system and Dennis Ritchie developed the C language. Both of these folks worked at Bell Labs. The UNIX operating system is still widely used today. It's the heart of Linux systems like Ubuntu and Red Hat. It's also at the core of the Mac operating system. And a lightweight version of it is used for the operating system on Android devices. The C language continues to be one of the most widely used languages today. That's because it's a high-level language, but it's designed in such a way that you still have a lot of control over the computer hardware, and in particular, memory. C is used whenever you need speed, efficiency, or hardware integration. For example, it's used for operating systems, graphic-intensive applications, and embedded systems. In the mid-1990s, Java was developed at Sun Microsystems. By the way, can you tell me who owns Java today if I give you 5 seconds starting from now? If you said Oracle, then you're correct. Oracle acquired Sun Microsystems in 2010. Both Java and JavaScript were developed in the 1990s, and I think it's important here to note that Java and JavaScript are two separate languages that have very little in common besides their name. It was entirely a business decision to associate them by name. In fact, Java has much more in common with the language C#, because when Java came along, Microsoft tried to extend and enhance it. So you might think that would be a good thing, but being Microsoft, the extensions and enhancements would only work on Microsoft products. So Sun Microsystems sued Microsoft, saying they couldn't call this enhanced language Java, and Microsoft finally decided to call it C# instead.